Okay, here we are with Lesson 3, Linear Functions and Proportionality. So let's take a look at Example 1. We'll be working on the lesson worksheet and in your math journal. What do you think a linear function, not a linear equation, is? Well, a linear function is likely a function with a linear relationship. Specifically, the rate of change is constant and the graph is a line. In the last lesson, we looked at several tables of values that represented the inputs and outputs of functions. For example, we have bags of candy and a cost. For one bag of candy, it costs $1.25. 2 bags is $2.25, and so on. Do you think this is a linear function? Justify your answer. Well, yes, this is a linear function because there is a constant rate of change as shown below. If we have 10 bags, or $10 and 8 bags of candy, then that is $1.25 per bag of candy. $5 for 4 bags of candy is $1.25, and $2.50 for 2 bags of candy is also $1.25. The total cost is increasing at a rate of $1.25 with each bag of candy. Further proof comes from the graph of the data shown below. A linear function is a function with a rule so that the output is equal to m multiplied by the input plus b, where m and b are fixed constants. If y is the output and x is the input, then a linear function is represented by the rule y equals m times x plus b. That is, when the rule that describes the function is in the form of y equals mx plus b, then the function is a linear function. Notice that this is not any different from a linear equation in 2 variables. What rule or equation describes this function? The rule that represents the function is then y equals 1 25/100 times x. Notice that the constant m is 1 25/100, which is the cost of 1 bag of candy, and the constant b is 0. Also notice that the constant m was found by calculating the unit rate for a bag of candy. What we know of linear functions so far is no different than what we learned about linear equations. The unit rate of a proportional relationship is the rate of change. No matter what the value of x is chosen, as long as x is a non-negative integer, the rule y equals 1 25/100 times x represents the cost function of a bag of candy. Moreover, the total cost of candy is a function of the number of bags purchased. So why do we have to note that x is a non-negative integer for this function? Well, since x represents the number of bags of candy, it does not make sense that there would be negative number of bags. For that reason, x as a positive integer means that the function allows us to find the cost of 0 or more bags of candy. Would you say that the table represents all the possible inputs and outputs? Well, no, it does not represent all possible inputs and outputs. Someone can purchase more than 8 bags of candy, and inputs greater than 8 are not represented by this table. As a matter of precision, we say that this function has the above table of values instead of the table above represents a function, because not all values of the function can be represented by the table. The rule or formula that describes a function can represent all of the possible values of a function. For example, using the rule, we could determine the cost of 9 bags of candy. However, this statement should not lead you to believe that a table cannot entirely represent a function. In this context, if there were a limit on the number of bags that could be purchased, that is, 8 bags, then the table above would represent the function completely. All right, let's take a look at example 2. Consider the following rate problem. Walter walks 8 miles in 2 hours. What is his average speed? Well, Walter's average speed of walking 8 miles is 8 over 2, which is 4, or 4 miles per hour. If we assume constant speed, then we can determine the distance Walter walks over any time period using the equation y equals 4 times x, where y is the distance walked in x hours. Walter's rate of walking is constant. Therefore, no matter what x is, we can say the distance Walter walks is a linear function given by the equation y equals 4x. Again, notice that the constant m of y equals m times x plus b is 4, which represents the unit rate of walking for Walter. In the last example, the total cost of candy was a function of the number of bags purchased. Describe the function in this example. You should have said the distance that Walter travels is a function of the number of hours he spends walking. What limitations do we need to put on x? Well, the limitation that we should put on x is that x is greater than or equal to 0. Since x represents the time Walter walks, then it makes sense that he would walk for a positive amount of time or no time at all. Since x is positive, then we know that the distance y will also be positive. All right, let's take a look at example 3. Veronica runs at a constant speed. The distance she runs is a function of the time she spends running. The function has a table of the values shown below. Since Veronica runs at a constant speed, we know that her average speed over any time interval will be the same. Therefore, Veronica's distance function is a linear function. Write the equation that describes her distance function. The function that represents Veronica's distance is described by the equation y equals 8 times x, where y is the distance in miles Veronica runs in x minutes, and x and y are greater than or equal to 0. Describe the function in terms of distance and time. The distance that Veronica runs is a function of the number of minutes she spends running. All right, example 4. Water flows from a faucet at a constant rate. That is, the volume of water that flows out of the faucet is the same over any given time interval. If 7 gallons of water flows from the faucet every 2 minutes, determine the rule that describes the volume function of the faucet. Well, the rate of water flow is 7 over 2, or 3.5 gallons per minute. Then the rule that describes the volume function of the faucet is y equals 3 5/10 times x, where y is the volume of water that flows from the faucet and x is the number of minutes that the faucet is on. Assume that the faucet is filling a bathtub that can hold 50 gallons of water. How long will it take the faucet to fill the tub? Since we want the total volume to be 50 gallons, then 50 is equal to 3 5/10 times x. In order to isolate x, since we want to know what number multiplies by 3.5 to get 50, then we do the inverse or divide. 50 divided by 3 5/10, which comes up to 14.2857, and it continues on and repeats. So in rounding it, we would get x is approximately 14 minutes. So it'll take about 14 minutes to fill a tub that has a volume of 50 gallons. Now assume that you are filling the same tub, a tub with a volume of 50 gallons, with the same faucet, a faucet where the rate of water flow is 3 5/10 gallons per minute. This time, however, the tub already has 8 gallons in it. Will it still take 14 minutes to fill the tub? No, it will take less time because there's already some water in the tub. So how can we reflect the water that is already in the tub with our volume of water flow as a function of time for the faucet? If y is the volume of water that flows from the faucet and x is the number of minutes the faucet is on, then y equals 3 5/10 times x plus 8. How long will it take the faucet to fill the tub if the tub already has 8 gallons in it? Since we still want the total volume of the tub to be 50 gallons, then 50 is equal to 3 5/10 times x plus 8. Again, trying to isolate the variable, we subtract 8 from both sides of the equation to get 42. And then 3.5 times some number is 42, and that would be 12. So it'll take 12 minutes for the faucet to fill a 50-gallon tub when there's already 8 gallons of water in it. So based on this, generate a table of values for this function. Well, you could generate the following. For 0 minutes, there would be 8 gallons of water. 3 minutes would be 18.5 gallons. 6 minutes would be 29 gallons, and so on and so forth. All right, let's go ahead and do example 5. Water flows from a faucet at a constant rate. Assume that 6 gallons of water are already in a tub by the time we notice the faucet is on. This information is recorded as 0 minutes and 6 gallons of water in the table below. The other values show how many gallons of water are in the tub at a given number of minutes. So for 0 minutes we have 6 gallons, 3 minutes there are 9.6 gallons, for 5 minutes there are 12 gallons, and for 9 minutes there are 16.8 gallons. After 3 minutes pass, there are 9 6/10 gallons in the tub. How much water flowed from the faucet in those 3 minutes? Explain. Well, since there are already 6 gallons in the tub, after 3 minutes, an additional 3 6/10 gallons filled the tub. So using this information to determine the rate of the water flow. So in 3 minutes, 3.6 gallons were added to the tub. Therefore, for 3.6 gallons, divided by 3 is 1 2/10. And the faucet fills the tub at a rate of 1.2 gallons per minute. Verify that the rate of water flow is correct using the other values in the table. Well, 5 times 1.2 is equal to 6, and since 6 gallons were already in the tub, the total volume in the tub is 12 gallons. 9 times 1.2 is 10.8, and since 6 gallons were already in the tub, the total volume in the tub is 16.8 gallons. Write the volume of water flow as a function from the time that represents the rate of water flow from the faucet. Well, the volume function that represents the rate of water flow from the faucet is y equals 1.2 times x, where y is the volume of water that flows from the faucet and x is the number of minutes the faucet is on. So write the ruler equation that describes the volume of water flow as a function of time for filling the tub, including the 6 gallons that are already in the tub to begin with. Well, since the tub already has 6 gallons in it, then the rule is y equals 1 2/10 times x plus 6. How many minutes was the faucet on before we noticed it? Explain. Well, since 6 gallons were in the tub by the time we noticed the faucet was on, we need to determine how many minutes it takes for 6 gallons to flow from the faucet. Well, 6 would equal 1.2 times x, and x would have to be 5. So the faucet was on for 5 minutes before we noticed it. All right, so now you have plenty of examples to look back on. Use those examples to help you with exercises 1 through 3. Complete the exercises one at a time and check your answers as you go by continuing the video. Okay, you should be done with exercise 1. Here are part of the answers. Stop the video, check your answers, and make any notes or comments on things that you don't understand. All right, here is the rest of exercise 1. And also the last part of exercise 1, part J. Then check your answers for exercise 2. Here's a continuation of exercise 2, parts B through E. And last, here is exercise 3. All right, let's go ahead and wrap this up. We know that a linear function can be described by a rule in the form of y equals m times x plus b, where m and b are constants. We know that constant rates and proportional relationships can be described by a linear function. And we know that the distance traveled is a function of the time spent traveling, that the volume of water flow from a faucet is a function of the time the faucet is on, etc. All right, see you in class.